So this is obtaining an empirical formula from experimental data. So another example, a sample of a compound is decomposed in the lab, produces 165 grams of carbon, 27.8 grams of hydrogen, 220.2 grams of oxygen. Calculate the empirical formula. So we take the masses of elements that were given, 165 grams of carbon, 27 point-ish, 27.8 grams of hydrogen, and 220.2 grams of oxygen. And we need to convert those to moles. So we want moles, we need to divide by grams, and so that tells us we need to find the molar mass of carbon. It's on the periodic table. 1 mole of carbon weighs 12.01 grams. So we do the math, we get 165, 165 divided by 12.01. Ah, good grief, I'm having issues here. 165 divide 120.01 equals, there we go. Shouldn't be that hard. 13.7. If we're counting significant figures, we should have 3. With these types of calculations, more is better. So definitely carry the 2 extras. So that would be moles of carbon. For hydrogen, again, I multiply by moles, divide by grams. The units are telling us what to do. I find the molar mass of hydrogen on the periodic table. So I've got 27.8 divided by 1.008. So this equals 27.5, 2 extra digits, moles of hydrogen. And then for the oxygen, again, multiply by moles, divide by grams, because that's what the units tell me to do. 1 over 16, 220.2 divided by 16. 13.7 625 moles of oxygen. Are you okay? I can't just use these as my subscripts in the balanced chemical equation. These aren't whole numbers, right? And I can't just round them to whole numbers. So I'm going to take the smallest of them, which is this 13.728. I'm going to divide all of them by that one. So this one divided by itself is 1. And this one divided by 13.728 . 13.728. This gives me 2.0089. And the bottom one, 13.728. This gives me 1.0025. We need to be careful when we round to whole numbers that we don't get ahead of ourselves. These are very close to the whole number, 2.0089. My rule of thumb is it's got to be less than 0.2 away. So if it's 2.1, you can round it. If it's 2.2, Don't round it. And we'll see an example where they don't end up being rounded. So we can call this 2, and we can call this 1. And those are the subscripts for the formula, which I didn't leave much room for. C1H2O1. And so that's the empirical formula for this compound. Any questions? Let's do another example. Ibuprofen has a mass percent composition. That's given here. Calculate the empirical formula of ibuprofen. This one's a little different because instead of giving masses of the elements, it gives us percent composition. What do? Well, the percent composition is the same regardless of the sample size. In order to find masses, we have to just choose a sample size. We can choose whatever's convenient. What's really convenient is 100 grams. Because if I have 100 grams of this ibuprofen, how many grams of carbon do I have? 75.69 grams. Okay? By choosing 100 grams, I can take a shortcut and just say 75.69 grams. I can just take the percent off and write gram, because that's true for a 100 gram sample. It's not magic, but it kind of seems like that. So I've got 75.69 grams of carbon. So 1 mole of carbon over 12.01 grams of carbon. So I get 6.3. I have to keep at least 4 sig figs. So that's moles of carbon. Then for the hydrogen, again, if I have a 100 gram sample, 8.80 grams are hydrogen. 8.80 grams of hydrogen. 1 mole of hydrogen is 1.008 grams of hydrogen. 8.8 divided by 1.008 equals 8.73. That one only has 3 sig figs, and then 2 extras, 1 moles of hydrogen. And 15.51% oxygen means 15.51 grams of oxygen in a 100 gram sample. Zero 0.9693. There's the 4 sig figs, 2 extras. Moles of oxygen. Okay. I choose the smallest and divide everything by the smallest. So that one divided by 0.969375 is 6.50135. And this one and then the last one ends up being 1. Can I round 6.5 to 7? No, I can't. So this is where we have to multiply by some number to get a whole number. 2. So 0.5 is the decimal equivalent of 1/2. Right? This is 6.5. If I multiply by 2, I'm going to get a whole number. If you understand that, awesome. If not, try 2. If that doesn't give you a nice number, try 3, try 4. So I'm going to take my 6.5, etc., times 2, and that gives me 13.0027. Plenty close. I can round this to 2. I can't. I can round that to 13. I also need to multiply the other ratios by 2. This one comes out to be 18.0119. Also, I can round that one to 18. And I have to multiply this by 2, and I get 2. The simplest whole number ratio here is 13 to 18 to 2. What we're doing here is a technique to arrive at whole numbers with minimal grief. You get the moles, and then to get these into whole numbers, you divide by the smallest number. That makes sure that everything is 1 or larger, and then you have to multiply all of them by the same number to get whole numbers. So these are then the coefficients, the subscripts. So C13, H18, O2. C13, H18, O2. Any questions?
So, for example, do we have to start with carbon? Do we have to use carbon's moles? Or
In terms of deciding what to multiply by?
Yeah.
No, you're going to use whichever one is not being a nice whole number.
Okay. What if there's 2?
If there's 2 of them, pick the one you like to start with.
I'll get the same answer.
You should get the same answer regardless. So it's entirely possible that you get 2 that are half, right? And both of them, if you multiply by 2, you're going to get a whole number. It's going to be an odd number. It probably won't happen in any of our problems, but it could. If things are not going well, go back and check your math. Because if you're using the wrong molar mass, or if you transposed a digit, that's going to really mess things up. Any other questions? This one is very similar to what we're doing in class today in lab. So we have a sample of copper reacting with oxygen to make a metal oxide. And we're supposed to calculate the formula of the metal oxide. So we have 2 elements here, copper and oxygen. What's the mass of copper? How much copper is in the example? 1.56. So 1.56 grams of copper. Oh, well, we can turn that into moles. 1 mole to 63.55 grams of copper. 1.56 divided by 63.55. 0.0, get a little better. 0.0245. That's the minimum number of significant figures. Moles of copper. What's the mass of the oxygen? Yeah, it's the difference. So this was the copper, and it reacted with oxygen, and now it weighs this much. Why does it weigh more? Because it pulled oxygen from the air, and now that oxygen is bonded to the copper and it's trapped. So the mass of oxygen is the copper oxide minus the mass of the copper. You're going to have to do that in today's lab to find the mass of oxygen. Because you can't measure, there's no convenient way to measure how much oxygen went into your crucible. So 1.95 grams minus 1.56 grams. 0.39. That's the mass of oxygen. So oxygen, and convert that to moles. And divide by 16. 0.024375 moles. Now you can kind of guess, can't you, that this is going to end up being 1-to-1? But I don't like guessing when points are writing on things, like on an exam. I'd rather not guess. So we'll divide by the smallest. Yep, as we suspected, this comes out to be 1.007, which we can round to 1. So this one is CuO. Okay? The point of doing this one is to show you that sometimes you're given a mass of one element and a mass of the product, and you have to find the mass of the other element by subtracting. If you use this as the mass of the oxygen, you're going to come up with something crazy.